Hi everyone. Um, the topic for today's uh, sort of meeting is Intro to Unsupervised Learning. Um, yeah, okay, next slide. So first of all, like what is unsupervised learning? So the main thing that makes unsupervised learning different than what we've been doing before is that it uses unlabeled data and it sort of discovers an algorithm or some sort of structure in the data itself. So we'll be going into more detail about AI that uses machine learning to analyze this unlabeled data and cluster them. And the way it does this is by identifying hidden patterns, different like behaviors, and this helps determine relationships. So the specific type of unsupervised learning that we'll be going into later is k-means clustering. It's one of the more simpler ones and is one of the most popular unsupervised learning algorithms. So here is just a quick visualization of sort of how unsupervised learning works. So you start with some data as input, and it's just a bunch of unlabeled data. So you have like no idea how to sort of partition it. And then there's going to be some algorithm, some way to like recognize or group this data, and that's sort of the output.
Yeah, so this is just another visualization of how unsupervised learning works. So here I just wanted to kind of emphasize, so like you see in the input data that the three colors that we're trying to separate are kind of like all interspersed, right? But what we can do with unsupervised learning is pick two different dimensions that represent this data in a way that allows us to separate them into different categories. So in a way, as Anisha earlier described, um, this is a type of like segmentation or also clustering algorithm. One specific type of algorithm that you guys might have heard of before is PCA, which stands for Principal Component Analysis. And what this does is actually really similar to unsupervised learning. It's a type of unsupervised learning. It basically allows you to visualize how your data looks before any processing. So yeah, I also just wanted to emphasize on how multiple times when you're trying to use data for like a real project that you're doing, not like just a pre-curated data set, you're going to be having to do something with unsupervised learning because your data ends up being unlabeled. So unsupervised learning a lot of times, though it's not talked about as often, actually ends up being like the main approach that you have to go to when you don't have proper data or you have to clean it up before you start processing. And it also allows you to just see trends in your data. Is it possible to actually run a supervised algorithm on it, which we'll be getting into with our Colab notebook? How do we determine the K value? Yeah, we're going to get into all of the stuff relating to K-means clustering in a little bit. We just wanted to start by kind of providing an introduction to like what unsupervised learning is. But yeah, we'll be going through all of like the theory. And also, as usual, if you have any questions, yeah, please put it in the chat and we'll respond to you as soon as possible.
Mhm. Okay, so now we can actually go into k-means clustering, which is sort of the main topic of our lecture. So k-means clustering works by clustering data points into groups. So first, we kind of need to learn some terms. So a centroid is basically the location of the center of a cluster. So this does not have to be a data point. It's just the general center of a cluster. And the amount of like centroids you have is basically the number of cluster centers you have. So just below in the picture that you see at the very bottom of the slide, we have like before k-means, you just have a bunch of unlabeled data. There's no way of determining how to group them really. And after k-means, you see that it's grouped into very specific sections. Next slide. Okay, so what exactly is the algorithm that is used in k-means clustering? So there are about like four different, starting with first, you just randomly initialize the k cluster center. A bunch of random centers are um, chosen. And then the second step is to categorize each point as part of the cluster whose centroid is closest to. So the points that are sort of like near a particular centroid is grouped into like one cluster. And once that is done, you update the mean coordinates after all points per cluster are assigned. And you repeat this until you have like a definite amount of clusters that isn't really changing. Um,
Yeah,
yeah.
and just to add on here, I want to emphasize on the fact that we randomly initialize the cluster centroid. So the actual location of where we start doesn't matter. It's kind of similar to how when we train a machine learning model, the parameters are just kind of randomly set, as we'll see when we get into deep learning. And then after, as you train the model, and in this case, as you place the points in the cluster that they're the closest to, you're going to update the points per cluster, update the centroid. So it's actually a really intuitive algorithm, but um, I'm sure like you guys are thinking of a lot of questions about like how do we pick the number of cluster centers? And as one of you put in the chat, like how do we pick the cluster centroid? So yeah, we'll be getting into all of that stuff in like a little bit. Um, are there any questions about how this algorithm works or anything before we move on? Or like how the updating or categorizing happens?
Yeah, there's actually a visualization on the next slide, so you can kind of see it. Um, okay, so here it's sort of walking through each step. So first, k random centroids are chosen, and then the data is assigned based on like which points are nearest to a particular centroid, and then this keeps on happening and updating until it's like split into like two definitive sections. Um,
Yeah, so step one occurs just once, and then you're going to keep repeating steps 2 and 3 until the centroid positions don't move anymore. So if you notice here, the centroids keep shifting across the screen as the points are assigned because they're moving to the relative mean of the coordinates that are closest to that spot. Yeah, we'll be coming back to this and kind of going through like an entire site that explains this in detail. So yeah, you will expect to see this again. Okay, so how can we measure how well a dataset or a model responds to k-means clustering? So what we can do is we can measure the distance between each data point and its assigned centroid. And then we can square this distance and then sum up the squares across each cluster. So that is what is represented by the formula on the top of the screen. We have n If we have n points, we're summing the distance between each coordinate and ck, which represents the centroid, and squaring it. So this is how we measure how well a dataset is responding. Ideally, what do we want? We would want to have a very low inertia because that means that each point is close to its cluster center and the centers are accurate. However, like if we were to have zero inertia, what does it mean? I'll pause here for a couple seconds so you guys can think about it. When can we ever have zero inertia? Yeah, exactly. So yeah, what it means is that every point is assigned its own cluster. So this can be thought of as analogous to kind of having an overfitting algorithm when you're doing supervised learning. So in that situation, your curve tries to fit too much to the data points. And yeah, this is an extreme case where every single point is its own cluster centroid. What does that mean? It's like not going to be helpful to a model. It's not going to be helpful in predicting any target column or anything like that, or grouping up the data based on certain features. So as you correctly pointed out, the extreme case is when we have zero inertia. But this means that every single point has its own cluster. So this means that there's actually a trade-off between minimizing the inertia of a clustering algorithm and having a low amount of clusters. Because obviously we would want a low amount of clusters such that our model isn't overfitting. As we increase the number of clusters, that kind of reduces like what our model is trying to achieve. But also you want to minimize inertia because you want the model to be accurate. You don't want to just have your data on one side and the cluster centroids to be somewhere random on the screen. So that kind of that's something that we always have to keep in mind when developing a clustering algorithm, and that is also something that we'll get into when we're looking at the Colab notebook. So to find the ideal number of clusters, we can use the elbow method, which we'll be elaborating on in the next slide. So low,
So
but not a 0K value. Exactly, yeah, because a 0K value is pretty
exactly.
much unattainable. You just want to minimize it as much as you can.
Okay, so to find the optimal number of clusters, we use this method called the elbow method. So essentially, you can graph the inertia on the y-axis and the number of clusters on the x-axis and see sort of the point where the rate of decrease in inertia begins to slow down. So what this really is saying is that there's not much of an improvement after the elbow point. So it's kind of like stagnated at one point, and that's sort of the number of clusters that you want to have. So in this particular graph, um, to the left, you can see that like at k is equal to 3, so at exactly 3 clusters, is where it sort of begins to slow down, the rate begins to slow down, so that would be the amount of clusters we want to use.
So just to pose a quick question, do you guys think that 3 is the only number of clusters we should try, or like why specifically 3? Are there any others that we should try that are nearby, or like why? Because it does look like from this specific graph, and we'll be like whenever you do an unsupervised learning k-means clustering, you're always going to get a graph somewhat like this, though the number of clusters will vary. In this situation, we should not only try 3 clusters, but we should also try 2 and 4. Exactly, yeah, because
Exactly.
we'd want to see what minimizes the inertia of our model.
Good
So,
point.
and also just to like reiterate on that a little bit, so why are we looking for where the rate of decrease in inertia begins to slow down? So that is a way of addressing the trade-off that I was talking about earlier. You want to find a number of clusters such that there's a significant change in inertia compared to the previous value, but after that point it starts to saturate. There's no point in really increasing the number of clusters, and that means that your model has already reached a satisfactory output and clustering. Do we have any questions at this point? Because this is kind of a subtle idea. I'll pause
Okay,
for a moment.
so I'll be putting a link in the chat um, that sort of explains a lot of these concepts and sort of the theory behind k-means clustering. Um, oh wait, there. Okay, so yeah, Ananya's pulling it up on her screen, but this is a great resource to sort of understand the theory before we sort of get into the coding aspect of this.
Yeah, so yeah, this site kind of just outlines what we're talking about with low inertia and a low number of clusters. So this is the graph that we showed where like 3 or 2 is the number of clusters. Here they say k is equal to 3 is the elbow of the graph, but many people would say it's 2 because that's kind of where you start seeing a sharp turn. That's why it's really good to experiment around that value. Um, yeah, so some possible applications of clustering. So there's obviously that aspect of segmentation where you want to group customers or group different topics, group different things based on a certain feature. So that's a very important application of unsupervised learning, and this shows up a lot in recommendation systems such as music or Amazon, things like that. Obviously, you want to also use them in search engines to group news topics and search results.
And these are sort of the steps that we were sort of highlighting in our slides on the particular um, steps sort of taken in the k-means algorithm itself. So could you scroll down? So yeah, okay, wait, stop scrolling down. Could
Yeah,
you?
so we just wanted to kind of share this resource so you guys can like go through it. Can there be any biases that go into k-mean clustering? I think I'm sure there is a way to do that, but you can like maybe make race or demographics like your target column and then cluster and see how much it maps to that. But I'm not entirely sure, at least with scikit-learn, if there's like a way to specify like a feature you want to cluster with. But there are more advanced algorithms beyond just k-means clustering that would allow you to do something like that. It's a very interesting idea, yeah. Okay, yeah. So you guys can like go through this and then let us know if you have any questions. But did we basically covered all of this in our presentation? But yeah.
Yeah, but we'll give you guys like a couple minutes to sort of read through it. Yeah, the scikit-learn library is like used a lot when it comes to like k-means clustering, and so yeah, it is used quite a bit, and we'll be using it in our collab.
Yeah, we've been using sklearn, I think, for everything up to this point. We use it for decision trees, not really much for the data preprocessing. That's primarily done with pandas, but most ML related things that are not deep learning, so like traditional ML approaches with classifiers, would be done with the scikit-learn library. Obviously, like you don't need to know like everything in it, but as you start using it more and you look through these collabs that we do, you get more familiar with the library and what it has. So we'll be getting into the collab very shortly.
Okay, so can everyone see my screen? Just put like a thumbs up. Yeah, that's perfectly okay. Okay, great. Okay, so we'll be starting with an example of unsupervised learning. Specifically, we'll be applying the k-means algorithm. So, as always, we have to start with sort of the data preprocessing and getting an idea of what our data set holds. So, we start with our imports. The specific data set that we'll be using here is the iris data set, which is a data set for flowers. And they're different, like the specific features in this particular data set is the sepal length, sepal width, petal length, and petal width. Um, great. So
Note here that because we're trying to do something with unsupervised learning, we're loading the flower type as a separate data frame. So this is because actually the iris dataset is, you probably heard it before, it's a really famous sklearn dataset and it's normally used for like supervised learning. But because we want to do something with unsupervised learning here, we're separately isolating just the X part without the target. Normally this is not the case, like you're going to be finding data on the web that you're trying to use without a target column or it isn't labeled, but in this case we're kind of curating that data set for us to use for this purpose. So yeah, this data only consists of 4 columns. We can try clustering with different sets of columns if you guys are interested. So yeah, we'll get started with that. So we're going to start with just doing the x.head method, which is going to kind of show us what's contained in the x data frame. If we scroll down a little bit, we can see it. Can you scroll down? Yeah, so as we've covered multiple times, the head method, what it does is it just shows you the first 5 rows. You can specify more or less if you want, and you could also just select how much of a data frame you need. Yeah, we
Hmm.
can try putting 10 or something to get a better feel.
So now it just prints out like 10 rows.
So the target column of the iris dataset is the flower type. So generally when you're training a supervised learning algorithm on this dataset, you feed it this information about the sepal and the petal, and then you ask it to predict what the flower type is. And there are 3 types of flowers in this dataset, 0, 1, and 2. I don't exactly remember what they correspond to, but they're different type of iris flowers. Yeah. And we have 150 samples, so 150 different flowers in this data set. It's not a very big data set, but we can definitely use it for this purpose. So as we emphasized in our data preprocessing notebook, every time before you start implementing a model, it's really important to visualize your data and understand it. So there are obviously different extents to which you can go with this, but because the main focus of this lecture is on k-means clustering, we decided to just do a simple scatter plot so you can kind of see how the data looks before we get into clustering. And also because this dataset is already an sklearn dataset, there is no need to normalize or do anything like that because it's already processed for us. So if we scroll down a little bit, you can see the plot and note that, okay, what we mean by normalize is you make it have 0 mean and unit variance. So that's just like a standard machine learning practice that you always do. You keep your data kind of like normally distributed with like a bell curve. You don't want it to be clustered around one point or have really wide outliers because that can significantly affect how your loss is calculated and things like that. Um, so the 2 columns that we've decided to use for this scatter plot are column 0 and column 1. And if you scroll up, or you can see right here, these columns correspond to the sepal length and the sepal width. So we just decided to pick 2 of these at random. After this, we'll go back and we'll experiment, and we invite you guys to also try putting different column combinations out of the 4 that we have and seeing how your clustering algorithm performs. So note here that we're passing in the hue to be df.column to 4. So just to pose a question, why might you guys think that we're doing this? Why are we trying to specify a hue and why this specific column?
So the question is basically why are we specifically choosing the hue to be like the 4th column? And also like what exactly does the hue really mean? Like just any predictions on what you guys think.
Just a quick hint, this might be based on what we want our unsupervised learning to kind of cluster to, what we want it to be. So note here that when we're doing columns of 4, it's actually not the 4th column, it's the 5th column. It starts with 0, so this actually corresponds to the target, which is flower type. But that's a good guess. So the reason why we're specifying a hue is because this is what we want our model to kind of predict too. We want it to cluster by these different flower types. But if you notice in this specific scatter plot, flower types 1 and 2 have a lot of overlap. It would be quite hard for a clustering algorithm to separate these two because it's hard for us to just by looking at it. So this might mean that These are not the best columns to experiment with, but we can try doing different combinations and seeing what the results are. Hello, I see Ishan has joined. No problem. We're going over unsupervised learning right now. Um, we just kind of went over what k-means clustering is, and then right now we're kind of going into how it works, and we're at the very beginning of our notebook. So feel free to type in chat or unmute if you have any questions or anything, and we can definitely go back and recap. Yeah.
So, any questions so far on just the basic data preprocessing stuff and how exactly the scatter plot works? Okay, great. That's the case. Oh well. Okay, great. So now we'll be going on to the actual elbow method. So as discussed in our slide presentation, inertia measures how well a dataset is clustered by the k-means algorithm. So could someone who was like in the meeting before this just like tell me like what exactly is the elbow method? Just like right in the chat, just to make sure you guys know what. So just like right in the chat what you think the elbow method is. Mm-hmm. Exactly. Yeah, exactly. So, and you can see this visually when you graph like the inertia and the number of clusters, and you can see visually where the point in which the rate of change begins to decrease. But yeah, exactly. So, um, the k-means is calculated. Okay, yeah. So it is calculated by measuring the distance between each data point and its centroid, as we mentioned in our slide, squaring this distance and summing these squares across one cluster. So in this code block, that's exactly what we're doing. So we're basically doing this the sum squared error and appending it all into one list with all the inertias.
So what we're doing, if you scroll up, we're actually looping between 1 and 11. So we're experimenting with clusters all the way between 1 and 11, and we're just running our model. km.fit actually does all of the training for us, which was the algorithm that we described earlier. We initialize the random centroids, we assign points, and then we move it to the mean of all of the points. So .fit does all of this until the model converges and the centroids don't move anymore. And you might be asking why 11? Well, that's because normally models would kind of tend to converge before that. 11 clusters is a lot, and this data only has 3 different types of flowers, so we would only kind of want to see around 3 to 4, maybe a little more than that, but nothing more.
And also note that we're doing it on the two features that we initially chose at the beginning, but we'll be experimenting with different features as we go through this notebook. Okay, so now we'll be implementing the actual elbow method, which, as I said earlier, allows us to find the number of clusters we should use in the actual algorithm. So just to summarize, there is a trade-off here because as we increase the number of clusters, the inertia will decrease. And the extreme case is when every single point has its own cluster, which means that the inertia is zero. And this obviously, as we mentioned earlier, isn't really possible. So we want to find the point where the decrease in inertia begins to slow, or where the increasing of k does not have much more of an impact. And also, as we mentioned earlier, but just sort of to recap, this is very like similar to overfitting in the sense that you don't want to have too many clusters because that's when you'll have the inertia to be zero, and that isn't really good when you're fitting an algorithm. So you want to sort of find the k where the decrease in inertia begins to slow, but it's not too low of a number. Um, any questions here?
So I realized that a possible ambiguity that you guys might have is why we might be having um, two columns that we're using for the clustering. So Anisha, if you scroll up a little bit. So here we're doing, as Anisha said, we're doing pm.fit on these two columns. But you might be wondering, can we cluster on more than just two variables? Yes, we definitely can, but for the purposes of this notebook, we decided to only cluster on two variables because that's the easiest to visualize. You just have two axes and you're trying to find a way to represent the data such that you can cluster based on just these two dimensions. If you have n variables that you're fitting on, that kind of means you're clustering in n-dimensional space. Also, because this dataset only has 4 features, specifying 2 is kind of more than enough for a clustering model.
Mhm. Okay, so as I was saying, we're going to be implementing the actual ALBA method here. So the way we're doing this is by using the Seaborn package, which is typically what we use for these sort of plots. And we're simply just plotting the sum squared error, or basically like the k-means, and the number of clusters in on the x-axis. So as we can see over here, we're going from 1 to 11 because, as Ananya mentioned, those are the number of clusters that we are trying for this. Um, and sort of by looking at this graph, what do you guys think would be the appropriate case to sort of test? So, like, which points do you think would be an appropriate elbow? Yeah, exactly. 2, 3, and 4 seem like appropriate points to try. Um, And also, if you look at this, like 5 also sort of seems like a possible point. So um, this is sort of where a lot of the experimentation is possible. But for we'll first be starting with having just 3 clusters, but then we'll be experimenting with 4 and 5, and we can also definitely try with 2 um, as we go on. Sorry.
It's not for the computer, it's for the iPhone.
Okay. Did you have a question, Sean, or? Okay, I'll just move on. So over here, we're doing basically the k-means algorithm with 3 clusters. Um, and this line is basically doing the entire algorithm of sort of like fitting it and of finding the appropriate clusters. Yeah,
Note
please
here
feel
that
free to type in the chat if you have a question.
to note here that when we're defining our k-means clustering model, we're specifying a random state. So what this means is the actual integer you put in doesn't really matter, but the fact that you're specifying a random state means that your cluster centroids are generated randomly. And this maps to the algorithm that we're talking about. We first initialize k random clusters, and then we repeat steps 2 and 3 of assigning points after that. So random state just means that we're picking random centroids.
Yeah, exactly. And just for curiosity, we can sort of print out what these cluster centers are. And basically, these are the x coordinates, these are the y coordinates. So we have like 3 different cluster centers, which we'll be seeing visually on a plot later. Does anyone have any questions at this point? Okay, great. So here we're just adding a column to our data set to sort of signify like what cluster that specific point was clustered into. So, and this kind of just gives us a way to see like what point, like what cluster each point is mapped to. So as you can see over here, we added a new column called cluster, and all of these points in just the first 5 rows of our data set were all mapped to cluster 2. Yeah, so we just used the inbuilt iris dataset, which is just, as Ananya said, a public SAILea dataset. Um,
And also, the reason why we're creating a specific column with df.cluster and then we're saying pd.series of k-means.labels. So k-means.labels is kind of an attribute of the k-means clustering algorithm itself, and it gives us access for each um, each x point that we have. It gives us a specific label corresponding to the cluster that it was assigned to. So if we add this to our data frame, as Anisha will explain in the next cell, we can create a scatter plot where we show how the clustering algorithm performs.
mhm. And also, Ishan, since you weren't here at the beginning, um, this is a link that just sort of walks through the theory behind um, the k-means algorithm. So feel free to take a look at that and sort of, um, yeah. Okay, so as Ananya was saying, we added the cluster column to our data set to sort of, because now we can use this to create a scatter plot to see how well it was able to cluster. And just to like re-emphasize something that we talked about at the very beginning in data visualization, this is how it should ideally be if it were to cluster properly. It should cluster in this fashion. So ideally we would expect to see something like this, but we'll see how it looks in just a minute. So in this one line, in these couple of lines, we're basically creating a scatter plot using, once again, the sepal length and sepal width as our x and y axes, and we're having our hue be cluster. Or well, in this case, so when we say 4, it's actually going to be the flower type, but we can change this to 5 to see how well the clustering algorithm worked. So I'm just going to run this cell. So we see by looking at this that the clustering algorithm didn't perform that well because it doesn't look very similar to what we'd want it to look like. But now, just to sort of see and compare side by side, I'll change this back to 4. Oh wait, I think I was burning the, yeah, over here. I'll change this to 4 so we can see how it's supposed to look. So if we were to cluster it based on the flower type. So as you can see, on this particular choice of using like sepal length and sepal width, it wasn't able to sort of cluster it properly. Um,
It was able
so
to
that
separate the flower type 0 though significantly, which is something good that we expected to see. But yeah.
that sort of leads to like the next factor of experimentation, which is like if we were to sort of do this entire thing, but change the features that we're looking at. But before we get into that, as I was saying earlier, we can first try changing the number of clusters we have for this particular choice of features. So here we're going to be trying it with n clusters equal to 4. We're basically doing the exact same thing, but we're just changing the number of clusters. Once again, I'm setting the hue to be 4 so we can see how it was able to cluster.
So note that when we have 4 clusters, we see 4 centroids, but in this sense, it doesn't really make sense to have 4 centroids because we only have 3 clusters that we're trying to predict. So in this situation, having 4 clusters, though it might cluster better, in this case it actually isn't. We don't really note any difference. There's no reason to really increase the clusters beyond this point. So that's kind of how we can settle that 3 clusters is the best to use.
Any questions on this? Okay, so now Ananya will be sharing her screen and we'll be sort of going through this process with choosing different columns.
So this is essentially an optimization method. Are you talking about the elbow method or just k-means clustering in general? Yes, the elbow method, exactly. It's just an optimization method. You're trying to figure out what's the optimal number of clusters to use. Okay, so we can now try experimenting with a different set of columns because in the case of using the first two, sepal length and sepal width, there really wasn't a significant difference or much of a clustering happening between the bottom section where we saw a lot of overlap. So what we can do is we can start by visualizing our data with columns 1 and 2, which correspond to the sepal width and the petal length. These are chosen arbitrarily, but we can see how the model will perform in this case. So here, just by looking at this scatter plot, we note that the data seems to already have a really nice and distinct labeling. So it should be easy for a clustering algorithm to work on this and figure out what the clusters are. There's still a little bit of overlap, as you can see here, between the black and the purple, but not too much as in the previous case, so a clustering algorithm might be able to separate these from each other. We can now run the elbow method while fitting our model on the other two features rather than sepal length and sepal width. So we would make it sepal width and petal length. And now we can just repeat the same step where we create a graph to visualize the elbow method and find the ideal number of clusters, which should also be somewhere around 3. So in this case, we note like significant saturation after 4, where the inertia doesn't seem to decrease much. It's interesting to note that between cluster 1 and 2, there's a very steep decrease, but this is expected because one cluster just means you're basically doing nothing to your data. You're just looking at it like the way it was originally. So what we can do is, once again, we can try a cluster of 3. Okay, I made a mistake. We have to change this to the 2 new columns that we're using. So every time you're making a change to your code or you're training on something else, make sure you're really careful in changing all places where you're using it because it's really easy to miss some. So now we've just fitted our model using these 2 new columns as the features to cluster on. And now we can see what the cluster centers are and visualize them the same way we did again. So you create the column corresponding to the cluster output or how each flower type was clustered. And now we can visualize how this looks. Once again, here we need to show with columns 1 and 2, because if we were to show it with 0 and 1, as I just did, the centroids look like they're in really random places. And why might this be the case? This is because the centroids, the coordinates specified above, they correspond to the location when our 2 features are sepal width and petal length. So that's why this looks really bad. So if we change it to 1 and 2, this would improve. So if you see here, our clustering algorithm performed significantly better. We can see that all three clusters were separated, the centroids located in the center of each cluster, and this means that our unsupervised learning model did pretty well in matching the target column. So if you compare this to what we had above, the actual target column, the clusters were mapped quite accurately with the centroids in the correct location. And note that this is with DF columns of 5, which means that it corresponds to our actual cluster centers. And they look almost identical, meaning that our model performed really well. We once again can try experimenting with a different amount of clusters. So in this case, we saw that 2 was surrounded by a rapid decrease on one side, so we can try experimenting with 2 and 4. So we can try 4. Before I move on, does anyone have any questions about why changing the columns makes it better or anything like that? Okay, great. So once again, we're going to be fitting on our new columns. So once again, it kind of, with the 4 clusters, we don't really notice a difference. We don't even see 4 distinct clusters actually, it just maps to our original 3 case. So this means that having 4 clusters isn't really a significant improvement, and sticking with 3 clusters is the best case. And once again, this makes sense because 3 corresponds to the number of possible flower types provided in the dataset. So that's about it for today's meeting. If you guys have any questions, as usual, feel free to ask us. Yeah.
Does anyone have any questions before we conclude this meeting?
And if you guys want to like review any of this again, there'll be a video posted on the SAILea website of the recording of this meeting, so you guys can like review any of the concepts again. Exactly, yeah, you can replace the iris data set with any other data set. But you obviously would have to change like the number of clusters you're using and everything, because that would mean you're using a different clustering algorithm.
Okay, great.
All right, thank you so much for everyone that joined today, and thank you Ananya and Anisha for another great course meeting. And I just wanted to let everyone know here that the meeting is going to be run bi-weekly, and we also have a schedule on our website under the course tab to see when the future meetings are going to be. And like a lot of people asked, to answer that, everything is going to be posted in the shared drive in the SAILea folder and on our YouTube channel. But if you do have any questions, feel free to reach out to us on Discord or email, and we'll be sure to answer you. And once again, thank you so much everyone for joining, and I hope you all have a great night.
Thank you.